Analysis of RL circuit. We have a resistor R in series with an inductor L. This is connected to an AC voltage source of frequency F Hz. The R and L form a complex impedance, an inductive load. An inductive load has a complex reactive component to it, known as the inductive reactance. XL is equal to 2 pi F into L. This inductive reactance causes the current to lag behind the voltage. That makes the inductive reactance along the negative imaginary axis. The total impedance of the load is Z equal to R minus JXL. We need to find out the current through the circuit and the voltage across the resistor and the inductor. Since all the elements in this circuit are in series, the current through them will be the same. Let the input voltage be V. The voltage across the resistance be VR and the voltage across the inductor be VL. We use small letter v to indicate the instantaneous values of voltages. At any instant of time, the input voltage will be equal to the sum of voltages across the resistor and the inductor. That is, V is equal to VR plus VL. Let I be the instantaneous current through the circuit. Let us draw the phasors corresponding to the voltage and the current in the circuit. Since the current through the element is the same, we will take it as the reference. Now, voltage across a resistor will be in phase with the current. So, VR can be drawn along the same axis as current. The magnitude of VR is equal to I into R. The voltage across an inductor will lead its current by 90 degree. So, VL can be drawn 90 degree upwards from the current axis. The magnitude of VL is equal to I into XL. The applied voltage V is the phasor sum of VR and VL. So, we can draw V like this. Here, VR, VL and V form a right angle triangle with V forming the hypotenuse. The angle between V and I is called the power factor angle of the circuit. It is represented by the symbol phi. This is the phase difference between the voltage and current. Since applied voltage is the known quantity, we take it as the reference. So, voltage V of t is equal to Vm sin omega t. The current waveform will have the same frequency as the voltage, but different amplitude and phase. So, I of t is equal to Im sin omega t minus phi. Let this be equation number 1. These expressions show that the current lags behind voltage by an angle of phi. Applying Pythagoras theorem to the voltage triangle, we get V square is equal to VR square plus VL square, which is equal to I into R the whole square plus I into XL the whole square, which is equal to I square into R square plus XL square. So, V is equal to I into square root of R square plus XL square, or V equal to I into Z, where Z equal to square root of R square plus XL square, which is the impedance of the circuit. So, we can write I equal to V by Z. Substituting this in the instantaneous expression for voltage and current, we get I of t is equal to Vm sin omega t divided by Z. Comparing this with equation 1, we can say that Im is equal to Vm by Z. Also, from the voltage triangle, we can write tan phi is equal to VL by VR, which is equal to I into XL divided by I into R, which is equal to XL by R, or phi is equal to tan inverse of XL by R. So, we have derived the expression for current in an RL circuit in terms of the circuit parameters.